Good afternoon, everyone. My name is Irina Zakharenkova. I am a space weather scientist in Cosmic Team, and I will chair this first part of space weather-related session. We have plenty of interesting talk, and I would like to invite the first speaker. It's Erin Lynch, and it's invited talk.
All right, good afternoon. I'm Erin Lynch from NOAA's Office of Space Weather Observations, and I'm very pleased to be here today to talk to you about the work of the task group on ionospheric radio occultation system optimization. So this is a CGMS task group. It's part of the Space Weather Coordination Group's work. So just to orient you in CGMS, whoops. Nope. So IRWG is in working group 2, which addresses data and products. And then the Space Weather Coordination Group is the group responsible for supporting continuity and integration of space-based observations to support operational space weather service providers. And then within that group, there are several task groups to address high-level priorities related to space weather. The group also sets the CGMS baseline for space weather observations, coordinates the space weather-related activities that take place within the various working groups, and just helps identify user requirements among the space weather community for CGMS. So within that working group, as I mentioned, there are 3 task groups, but the work also spans a few other groups as well. So within working group 1, there's a new task group that was formed to address the issue of space environment sustainability, which has a lot of overlap with space weather. There's also coordination with the G6 intercalibration group for space weather. And then within the space weather coordination group, task group on spacecraft anomalies, on improving access to space weather data, and then the ionospheric RO optimization task group. And you'll notice one name appears many times, Andrew Monham from EUMETSAT. He's the task group lead for many of these and has been the task group lead since the start of the ionospheric RO optimization task group. So all of the work that I'm presenting is really thanks to his leadership of that group, and I'm pleased to take over this coming year and take one thing off his plate. So the Ionospheric RO System Optimization Task Group was formed to address the high-level priority item 6.4. And that reads, in coordination with IROWG, establish requirements for and recommend an implementation of an optimized system for radio occultation observations for ionosphere monitoring. So obviously, this aligns really well with some of the objectives of IROWG and the space weather subgroup in particular. And our task group really benefits from the support of ionospheric RO experts, representatives of the various CGMS member agencies that are RO data providers, and coordination with IRWG. So over the past, I think it's been 2 years, maybe 3 years since the task group formed. It's made a lot of progress in documenting the current capabilities that we have from RO missions, reviewing methods to geolocate plasma bubbles and scintillations, and initiating some limited number of observing system simulation experiments. So this task group just has that one action to establish the requirements and recommend an implementation for radio occultation for ionosphere monitoring. And so within that, the group has several objectives. So they're looking at establishing requirements for data latency. The number of counts obviously is an important metric across RO observations. So establishing the right number for ionospheric applications is important, and looking at the geographic and local time coverage requirements to support ionosphere applications. And so to establish those requirements, the group is also looking to define OSSIs in order to understand how sensitive operational ionospheric applications are to changes in those requirements. And a key component of that is assessing the commercial RO capabilities that can help support the requirements. So as I mentioned, the membership of this group consists of representatives of the various CGMS member agencies, scientific working groups, and space weather service providers. And so we would welcome nominations from any of those organizations, and IRWG in particular, so that we can increase the level of coordination we have between these two groups that are working towards similar aims. So this is the list of membership from last year, and so we'll update that going forward. But if you're interested, please reach out. So a little bit more detail about the activities that we're undertaking. So the terms of reference defines what's in the scope of work for this task group. So a lot of effort over the past 2 years has been put toward number one, which is reviewing the current implementation of the existing RO missions. And so that's tracking, how many ionospheric measurements they're making, if they happen to have ionosphere capabilities, what orbital planes they're covering, and what latencies they're able to achieve. User requirement definitions. So as a operational space weather agency, our requirements come from the operational users. And so we're also looking towards possible improvements that could be made to members' capabilities to improve, how low latencies they're able to achieve, similar things. And then toward that, the definition of OSSEs and observing system experiments, again, to look at the sensitivity. And here's where I think work is really needed. And we've seen how important OSSEs have been for the neutral atmosphere in helping to understand what the impact of radio occultation measurements is and how that correlates with the number of observations that are available. And so continuing to expand those capabilities for space weather so that we can do the same kind of looks at our requirements is really important. And then finally, we really want to incorporate the impact of commercial RO that have space weather capabilities. So now I'll talk a little bit about some of the work that NOAA has done towards these objectives. So not only does NOAA respond to the international community's interest in radio occultations and understanding the requirements there, but NOAA also wants to understand the need for ionospheric observations. So this will feed into commercial data buy requirements and assessing the need for a potential RO backbone. So what I'll present here is just a very preliminary assessment of the number of RO observations that might be needed to support modeling capabilities. A lot of work remains to be done. So as I mentioned, NOAA derives requirements from user needs, and in this case, users are operational space weather service providers like NOAA Space Weather Prediction Center. And those requirements are captured in the Consolidated Observation User Requirement List, or CORAL. So here's the entry related to TEC. And you'll see, if you're familiar with Cosmic 2 capabilities, there's a lot of overlap. In fact, these requirements are derived from providing continuity with Cosmic 2 in some cases. So the measurement accuracy is very familiar, the measurement range, the geographic coverage, global rather than the tropics, provided by Cosmic 2, and the count of TZ occultations with a threshold of 12,000 relates to that, if Cosmic 2 had 2 components. You'll notice the data latency is quite high. This comes from a generic recommendation for latencies from a LEO satellite. So this is something we're working to improve, to align better with what we know the needs for latency for the ionosphere are. But we also suspect that perhaps that count, which is based on, as I said, capabilities, is perhaps low to support operational RO applications. So as a first approach for addressing what this requirement might be, we're considering just a single application, which is using TEC in order to support modeling the background ionosphere through data assimilation. So we didn't look at separate cases for quiet and disturbed geomagnetic conditions. And I'll also present an OSSE that was conducted on behalf of NOAA. But this OSSE did not look at constellation optimization, so it didn't really explore the impact of increasing specifically the number of observations. So in order to provide a global refresh of TEC, we made a couple of assumptions about the modeling scenario you might want to support. So for example, if we have a 5x5 global model and a 2-hour assimilation cycle, which probably needs to be even faster to capture the temporal timescales of the ionosphere. We just did a simple back of the envelope calculation of how many observations you would like to have so that you're able to update all of your grid cells each assimilation cycle. And you need at least, well, more than 30,000. So that's considerably more than the 12,000 that we're carrying as a threshold requirement, but within the objective. And of course, more work will need to be done to test the validity of this assumption. This doesn't take into account how those observations are assimilated, if they're treated as points, if you're assimilating just the electron density profile derived from the TEC occultation. So this is, again, just a simple, quick estimate. And as I mentioned, we did do one OSSI, although this was looking more at architectures rather than the actual requirements. So it wasn't testing the number of occultations. But this was conducted in 2022 by Tomoko Masuo from UC Boulder. And she assimilated electron density profiles into the TIE-GCM model. And those profiles were simulated using WAM-IPE as the nature run. And she used the DART implementation of the ensemble adjustment common filter for the data assimilation scheme, and looked at both quiet and storm periods around the 2015 St. Patrick's Day storm. So here she looked at a number of constellations. So they were based around cosmic 2 constellations. So one segment was 24-degree, or had 6 orbital planes at 24-degree inclination, 520-kilometer altitude. So that's like cosmic 2A. And then another segment at 800 kilometers and 72-degree inclination, like cosmic 2B. And then kind of the reverse of that. So a low altitude, 72-degree inclination constellation, and then a high altitude, so 800 kilometer, 24-degree. And then a number of combinations of those two. So so some experiments just had one segment, 6 satellites, and then 6 of those had as many as 12 satellites. So the way that the performance was evaluated is she constructed a ranking metric that looked at each OSSI's relative performance. So the TIE-GCM that assimilated the observations for the specification was compared to the WAM-IPE truth and looked at a number of metrics to see how well the model was representing certain features. So the height of the F2 layer, HMF2, the peak density of that layer, NMF2, as well as TEC and the altitude electron density. And then ranked each of the 10 scenarios based on the RMSE of each of these parameters over certain latitude regions, and then average those together to kind of rank the overall performance. So here's a scorecard representing that. So in this case, 1 would be the best performing scenario, the best performing constellation, and then that's represented by green, obviously, and then as they get more red and closer to 10, those are not performing as well. So what she found was that where there are more observations for a given latitude band, there's better performance. So that's exactly what we hope. It's supporting the specification ability. And we see better performance from the constellations that include components at 520 kilometers because they produce more occultations than the constellations at 800 kilometers. And the observations were able to help improve the model biases that are present in TIE-GCM, especially about the equatorial ionization anomaly. And so I'll just go back to this figure here. So if this is the truth, and here's the control where no assimilation was performed, here are 4 constellations. So this one is like Cosmic 2 that we have currently. This would be the high inclination, higher altitude constellation. And then here's kind of the reverse. So if Cosmic 2A were at 800, and if I believe this should say 500 if Cosmic 2B were at the lower altitude. And you can see that, it better represents this feature here, which is that equatorial anomaly when those observations are assimilated. I think you've heard earlier this week that NOAA, maybe it was last week, is considering an AOA to look at the observing system needed to support both neutral atmosphere and space weather applications. And so in an early phase of this, the UCAR team working on it did look at simulated TEC observations from the various constellation configurations to look at the coverage and refresh. And so we're really looking forward to the next phase of this study, which will evaluate the space weather requirements in more detail. And another important consideration is, the scintillation as well. And I think the next phase of that AOA will look at that. I won't spend too much time on this because I think Paul's speaking about the coverage and refresh needed to support the scintillation products that have been enabled by Cosmic 2. So I will summarize here. So the task group has done a lot of work over the years to understand the current capabilities of radio occultation systems that are making space weather observations. They have identified some inconsistencies with the OSCAR database, which also tracks those. And so changes will be made shortly to bring everything into alignment. We'd really like to assess commercial capabilities in the coming years. So if you're a commercial provider with space weather capabilities, please come talk to me so we can make sure that those are tracked accurately and can be factored into these exploration of future radio occultation observing systems. And there's a lot of, there's a lot of work to be done, still defining OSCEs to help understand the requirements for ionosphere applications. And we're really looking forward to increased coordination and collaboration with IROWG and the space weather subgroup in particular. We've had a lot of good conversations over the week, and we've made some plans to keep that going. So thank you so much for your time.
Thank you very much. We have time for 2 questions.
So in terms of the study that was done with the time GCM or TIE GCM, how is the data ingested? Is it, is the RO data treated as, obel inverted profiles, or is it as slant path TEC?
No, so she used WAM IPE to simulate the slant TEC, so integrate along the signal path through the model and then inverted that TEC.
But so you got this good simulated TEC from your truth data.
Right.
How is it ingested into time TIGCM?
So it's ingested using the data assimilation. So the observation weighted by errors, she derived the errors by looking at how the retrieved electron density profile from that inverted TEC simulation compared to the actual electron density. Yeah.
So she performed an obel transform
Yes,
and ingested that.
Yes.
As opposed to ingesting slant path TEC.
That's right. Yeah. Turn the TC into the obel inverted electron density profile.
But my comment would be that that's not optimal, of course, right? Really should be, because you're getting errors from the obel.
Yes.
When you would do that ingest.
Yes. Yeah.
And perhaps that explains some of although you did better when you had more data, still the equatorial was not really matching.
Right, and that's where your assumptions about the spherical symmetry are the least valid. So absolutely, and I think that was chosen one because the electron density profile aligns most closely with the model state, and then also because you do get the errors introduced by that. So she didn't add any additional error; you just have the error, the systematic error introduced by the obel inversion. Did you want to say so?
only short, very, very quickly.
Oh.
Jonathan Brandmeier from Planet IQ. I just have one very quick remark about commercial capabilities. Capabilities that go above and beyond which orbits the instrument platforms are operating on. It also goes to which features are available to those instruments. To your question, what do we have? Our answer is, what do you want? No, really.
Yeah, we'll talk for sure. Thank you.
We would like to invite the next speaker is Mark Kasparon from NOAA.